Good morning, everyone. I hope you guys are able to see my screen. I'm audible. Let's get the class started for today. To begin with, any questions, doubts?
Sir,
Yes, Onkar?
in the last lecture,
Mhm.
we discussed how B1 and tau p are both adjustable parameters,
Correct.
but then we also found an explicit relation between tau p and B1. So
Wonderful.
while
Correct.
doing while doing an actual experiment, which
Yeah.
parameter exactly do we control, or is it like both can be controlled?
Excellent question. So as to get everybody else to speed, let me write the pertinent relationship which you are trying to refer to. Very good question, Onkar. This is the expression that you're trying to refer to when you're trying to get a certain flip angle. I was mentioning that B1 and tau p are parameters that you have control over and which one should be changed. This largely depends upon what you want to achieve. For instance, this is a definition I avoided trying to give, but let me give it right now. When you want to achieve a hard pulse, what is a hard pulse? Bandwidth of excitation is greater than the spectral width. If you don't remember what these are, influence of the pulse is greater than the window of frequency you want to observe. Let's take the typical example that we took off in the class earlier. If you want to look at a 10 ppm spectral width between 0 to 10 ppm on a 500 megahertz, your spectral width is 10 times 500, which is 5 kilohertz. And let's say you're applying a high power 10 microsecond pulse for 90-degree flip, then the bandwidth happens to be 25 kilohertz. Is that the example that we saw earlier, Omkar?
Yes, I believe it
Okay.
is.
So if you want to achieve a hard pulse, you realize that the B1 that you apply is much greater than the spectral width that you have. So this is called a hard pulse. So at that moment, what you tend to do is to keep the pulse at as high a power as possible in the spectrometer. What do I mean by this? Of course, this is a number that I got after set a maximum B1, but it goes both ways. As you rightly pointed out, there is something called a time bandwidth product. You see, that is the tau p part of it. This is the B1 part of it. Remember, time and frequency are inversely related, and due to the uncertainty principle, they share a certain relationship based on the shape that you apply. And for the rectangular shape of the pulse, so what do I mean by this? This is something I didn't draw yet, where until you start the experiment, meaning that until you start the perturbation, there is no B1 field. And then after a point, you apply a constant B1 field for a duration of tau p, achieving whichever flip angle that you want, and you turn it on. This is called a rectangular pulse. Okay, we often refer to as rect pulse. So for a rect pulse, if you want to achieve something like a hard pulse, you would keep B1 as high as possible, which is hardware dependent. All these are based on the amplifiers that you have. For something like Proton, the amplifiers would be like a 10-watt amplifier. If you're not able to follow some of this, do not worry about it. When you set the same experiment for the same sample in multiple spectrometers, this will become a little more clear to you. So at this moment, you would want to keep B1 as much as possible on the spectrometer and then calibrate for tau p to get the desired flip angle. If you're still not able to follow it, it's like, let's say you have two different bikes. One is a simple bike that will go up to, say, 50, 60 kilometers per hour very easily, but not any higher. On the other hand, there is another bike that can easily go to 100, 150 kilometers per hour. Okay, pretty sure you would want to use the 150 kilometers per hour bike so as to go faster to your destination. But not always going fast is your interest. There are also other aspects. Let's say you want to deliver many things, you would rather take the slower bike than the faster bike, so that you make sure that you don't unnecessarily reach peak power. So of course, the opposite of the hard pulse is a soft pulse, where bandwidth of excitation is lesser than the spectral width. Okay. For instance, you may apply some B1 fields as low as say 250 hertz with a spectral width being something like 5 kilohertz. Why would you want to do this? Recollect that in a spectrum you have multiple resonances, and for whatever reason you want to hit one of the resonance. The classic example of this is water. In all your biomolecular samples you will have water, and remember, water concentration when it comes to protons is to the tune of 110 molar, and the biomolecule concentration will be in the tune of say 1 millimolar. And you are able to already understand water is 5 orders of magnitude higher in concentration, and therefore you need to kind of kill water. At that point, you will end up invoking something like a soft phase. I'll try to come back to this later. At this moment, you would actually use a lower power pulse for a longer duration. So remember, if this goes 2 orders of magnitude lower, the pulse width has to go 2 orders of magnitude higher, and therefore it will go 1000 microseconds. Therefore, it will be a 1 millisecond pulse applied at 250 hertz so as to achieve a certain flip angle on resonance. Okay, so the long and short of it is that this is an attribute of the spectrometer. If you want the hard pulse to be executed, you set it to the peak power from the spectrometer and try to calibrate for it given the alpha that you want. On the other hand, for a given spectrometer where B1 maximum can be achieved, you can reduce B1 and increase tau p to get the same effect, which is also what we saw in the simulation, which I'll come to in a moment. Okay, so you have control over both of this. While this is something that you have a maximum limit for in a given spectrometer, on the other hand, this is something that you calibrate based on what you want. Maybe I'll show an example of an experiment once I'm back in Bhopal online, then we can understand this better. Maybe even today, let's see whether I can log into my instrument and show it to you. Okay?
Yes, sir.
Okay, good. Any other questions from others? Feel free to ask. I'd like to iterate that the whole purpose of this course is to keep it engaging in the sense like if you don't understand something, which could be the case for many, this is your forum to raise your question so that I can try to explain it the best possible way. And you may feel free to ask, I still didn't understand, explain again. I'll be happy to explain. Yes.
What decides the direction of delta V naught? I mean, you said that
Right.
the opposite is positive, then the direction of delta V naught is positive and vice versa.
Right.
Clear.
So do you remember this example that we took in the class where we had 3 resonances at 1 ppm, 3 ppm, and 4 ppm, and we kept the carrier at 3 ppm? Do you remember this example?
Yes.
I couldn't hear you. Do you remember this example?
Yes, sir.
Okay. So if you see here, we set the carrier on 3 ppm. The moment you do this, the 1 ppm has a negative delta B naught, because delta B naught goes as something like minus omega, or rather, I could take either one. Let me make sure my definition is right. It's morning 5:30 here. I just woke up so that we can do the class, so I don't want to make a mistake. That is it. Here it is. So that's the dependence. I would have written it more explicitly. Let me see where I've written it. Yeah. Just a moment. I never wrote delta V naught. Okay. Is it minus capital omega by small gamma, or what is it?
minus capital omega by gamma, yes.
Yeah, there you go. I have written it. Yes, minus capital omega by gamma. So the moment your capital omega is greater than 0, do you realize your delta B naught is in the opposite direction? You have a negative sign along the k cap vector. What does this mean is that, remember that for a molecule like ethanol, which has multiple resonances, you will have multiple M naughts, one coming from CH3, one coming from CH2, and another from OH. And therefore, for OH, there will be no delta B naught. CH3, there will be some delta B naught. And let's say CH3 delta B naught was like this, assuming it was 2 ppm away. On the other hand, for the hydroxyl, the delta B naught will be pointing in this direction. Yet again, I want you to remind yourself of the merry-go-round example in the mom. Right now, the merry-go-round is going at a certain frequency, and the mom is going at a certain other frequency. If omega naught is greater than omega RF, there is an apparent motion where the merry-go-round still is going in the clockwise direction. On the other hand, if your omega naught is less than omega RF, then it appears that the entire direction will be reversed, apparently, for between the merry-go-round and the mom. Let's say omega RF is greater than omega naught. As time progresses, it will be as though for the hydroxyl resonance, the motion is opposite to that of what you have for metal. On the other hand, the methylene would remain unchanged as a function of time. Okay, so that decides the entire direction of delta B naught being positive, 0, or negative.
Okay, sir, understood.
Okay, any other questions from others?
And sir, what is the meaning of the flip angle alpha being negative?
Flip angle cannot be, it could be, see, angle could be negative based on how much movement has happened to M naught when you begin the experiment, sorry, to when you have finished, not begin the experiment, when you have started the pulse and when you are finishing the pulse. You can always flip M naught by pi by 2 to get it along 1, or you can do it by minus pi by 2, which could be 3 pi by 2. 3 pi by 2 is minus pi by 2. So these are all due to periodicities. Flip angle is merely the angle subtended by the magnetization before and after the pulse. Generally, for biomolecular NMR, we'll have 90 degrees and 180 degrees that are commonly applied. There could be experiments where 45 degrees, 135 degrees are also applied along one of the phases, X phase of like this. Okay, so flip angle could still be negative. You executed something like a 270-degree pulse. Okay. I see Deeptanu has raised his hand. Please go ahead, Deeptanu.
Yes, sir. So in the last lecture, you said like we generally calibrate tau p with a 360-degree pulse. Like here,
That's right.
360 refers to the flip angle.
That's correct. 360 degrees refers to the flip angle. You're totally correct.
Why is that? Like why 360?
Huh.
And
Very good
also, like
question.
another question,
So
like
one question
you.
at a time. One question at a time.
Yes, sir.
Then I'll forget the question. Okay, let me write down. Why tau p is calibrated with 2 pi flip angle. Okay, next question. Carry on. What is the next question, Deeptanu?
You referred to like the oscillation of mx as like sinusoidal. That's also probably
No.
related to this.
Mx of t. I don't know. Maybe you probably read this kind of a function. Is that right?
No, you showed like the plot actually. Yeah.
So basically, on the simulation, there is the plot that goes here. Is that right?
Yeah.
That's
Yeah,
what
you
you're
also
referring
drew
to?
it. Yeah.
So where you had a plot that keeps going sinusoidal on the top right corner of the simulation. Is that what you're referring to?
Yeah, yes. You also drew it
I,
in your class.
oh, no. You see, you're confusing between FID and oscillation. I'll come to each one at the moment. Let's ask the
Okay.
first question to understand what we are trying to do. That's a very
Yes.
relevant question. you could always calibrate a flip angle at 90 degrees. You would soon realize that just because of this dependence, you would end up getting a maxima at alpha equal to pi by 2. But there's a small issue when it comes to spectrum that you end up acquiring. Let's just take water, for example. It's not the best example to understand how you calibrate, because calibrating on water is difficult. I'll come to it in a moment, because the concentration is so high, it has other effects. Generally, you would calibrate on your solute. What do I mean by that? Let's say you put ethanol in, say, D2O or H2O. You would look at the ethanol resonances to calibrate, not the water resonance. But water still has only one resonance, and we can keep it on resonance. So it also makes your life easy not to worry about the off resonance effects. Now let's say that you're trying to optimize for the flip angle. So let's try to plot how the magnetization will change as a function of flip angle. Okay, and let's assume that you're applying an alpha Y pulse. What do I mean by this? You are applying the B1 along the Y-axis with omega RF within, where the offset is 0. Okay, you're keeping it on resonance. Shall we assume that, Deeptanu?
Yes, sir.
Okay, so now what happens is that, let's say you applied a 0 degree flip angle. You agree that no signal would have come. You agree with me?
No signal as in
No pulse is applied. See, what's a
okay.
0 degree pulse is when you set
The
tau p to 0.
magnetization does not change. Yeah.
Yeah, magnetization doesn't change. And
Yeah.
if the from thermal equilibrium, if you start, the magnetization does not change. Would you measure anything in the transverse plane?
No.
Exactly. No. So therefore, you get no signal to begin with, right? And therefore, let's say you apply a 90 degree pulse. Let's assume you get a maximum of this sort, right? We also saw an example where we flipped it to 180 degrees. Correct? Did you see
Yeah.
any oscillations after the application of 180 degree pulse?
In the simulation, I don't remember.
Yeah. There'll be no signal because you would have taken entire. So what happens when you apply 180 degree pulse? The P beta becomes greater than P alpha.
Yeah.
Remember the condition that you started off with, the thermal equilibrium, was P alpha greater than P beta. After you applied the 180 degree pulse, the polarization gets entirely transferred in a way where you have a negative polarization. So therefore, I'm also not, yeah, so therefore, you're going to get 0 signal at 180 degree pulse. Correct?
Yes, sir.
Okay, I have to be a little more clear where receiver is kept along the x-axis. This also I should be clear. Because if you apply a 90 degree pulse along y-axis, the entire m0 will be along the x-axis, giving you maximum signal. And therefore, this is the dependence. Okay, now let's continue this thought experiment. And let's say you apply a 3 pi by 2 pulse. What is going to happen? You're going to have the entire magnetization that comes up along the minus x-axis. Is that right?
Yes.
Counterclockwise rotation. So therefore, you're going to have a signal that goes like this. Continue the whole idea. 2 pi pulse is a 0 degree pulse. So you're going to get no signal. If you actually do a more fine-grained analysis of this, where you take 45 degree, you can take literally for every 1 degree, you can get the signal out. And therefore, you're going to get a sinusoidal dependence. So then I told you, wherever you get a 360, where you have a 0 crossing, you take that divided by 1/4 to get the actual tau p for your pi by 2 pulse. That's your question. Why did we choose 2 pi? Why did we choose pi by 2? Correct?
Yes, sir.
Itself. Multiple things. The phase that you get your signal in NMR is a relative phase. Although we keep saying we can keep the receiver in x-axis, these are arbitrary phases based on how the pulse ends up being applied. And as you go further, you will realize that you will never get an NMR spectrum which is fully phased. So after you get it, you do something called phase correction. I'll try to show that today. Once you do the phase correction, you know what is the actual phase. And remember, therefore, any phase that you get negative could also be phased to positive because it's a relative phase. And that's a problem. So generally what we tend to do is to pick up a short flip angle, face the spectrum, and repeat this entire analysis to see how the sinusoidal part works out and pick up the 2 pi degree. That's actually the way to do it. And there's a reason. You could always say if you want a zero crossing, okay, let's first ask why a pi by 2 calibration is not done around pi by 2. If you take the function of sine alpha, you would know that alpha is maxima, attains a maximum at pi by 2. But you would also appreciate as alpha tends to pi by 2, be it getting close to 90 degrees or going away from 90 degrees, but very close to 90 degrees, you'd see the value of sine alpha is very close to 1. Okay? And even when you're getting a signal, remember there is noise associated with signal. So this noise would not let you distinguish something like 0.99 versus 1. Okay? Meaning that the slope at which this part is not very high. But with the same argument, the slope that the function undergoes close to pi is very high, meaning that it goes from positive to negative, so the slope is going to be very high. So you could always argue we could calibrate the pulse using 180-degree pulse. Okay, because it's very sensitive to see the signal. If you face the signal positive here, at this point of time, you'd have small positive, you'll have negative. I mean, you will have 0 at 180, then you'll have negative, more negative, very negative. Then you'll be able to get this. So you could also calibrate the pulse at 180-degree pulse. But there is a small problem. I mean, first thing that you have to do is to just divide the 180-degree pulse width by 2. Tau, whatever you get here, tau p can be achieved by halving the pi pulse. Currently, what we are doing, getting 2 pi and dividing it by 4. You could always get the pi and divide it by 2. So far, so good, Deeptanu?
Yes, sir.
But we do not prefer a zero crossing around pi, and we prefer the zero crossing around 2 pi, because if you end up applying a pi pulse, do you realize, or at least close to pi, your m naught flips and is pointed towards minus z-axis, correct?
Yes, sir.
And remember, I told you T1 is many times much larger than T2. Therefore, if T1 is of the order of say 2 seconds, after a 180-degree pulse, you need to wait at least until 5 times 2 seconds, which is 10 seconds, before you can repeat the experiment to signal averaging. Recollect the fact that NMR is an intrinsically insensitive experiment, and therefore the noise is going to be not letting your signal be high. So when you repeat the experiment, you get slightly high. When you repeat the experiment, you get even slight. So you want to do signal averaging so as to make sure you figure out what's a signal and what is noise. So you want to repeat that experiment several times to get your signal. And if you have to wait for a delay between scans to be 10 seconds, that's a very, very long time. Alternatively, if you're trying to do around a 2 pi flip angle, you are immediately able to understand it is very close to thermal equilibrium. So your D1 times can be say 1 to 1.5 seconds. That itself is a lot. And then the magnetization would have required very close to thermal equilibrium. So therefore, the zero crossing around 2 pi for the proton dimension is most preferred, largely because you'd be able to repeat the experiment several times faster to get the calibration done. Did that answer your question? Why do we calibrate around 2 pi and not around pi by 2 or pi?
Yes, sir.
Did everybody else understand? The Pune and Thiruvananthapuram guys, please raise your hand and say on Zoom. And the Bhopal guys can say yes or no.
Yes, sir, I understand.
Okay. The rest, Gauri, Onkar, Priyadarshini, Deeptanu, Anjali, and Purab, if you understood what we just discussed right now, please raise your hand on Zoom. Or you can unmute and say you understood. Yes, I see 2, 3, 4. Okay, all right. I think most of you got it. My request is not to lower the hand until I ask you to lower it, because otherwise I cannot see who is raising and who is lowering. Okay. All right. So that's how we calibrate a pulse. Let me try to see whether we have enough time. It's just 9:26. Suman, I request you to remind me by 9:50 so that I finish the lecture by 9:55. Okay. So now I'll try to answer this part of the question. Why are you getting an oscillation? Whatever oscillation you're getting, there is something else. That's a signal that you end up acquiring. Let's go back to the simulation, shall we?
Is it just because we are measuring the transverse component?
You're measuring only the transverse component, correct? So what's your question? I'm sorry, I still didn't get the question, but I can do a simulation and you can see how it goes.
So, you had said like we do a point by point multiplication of an exponentially decaying and a sinusoidal.
Okay, I'll come to that. Okay, good. So it's always good to take a look at the simulation and understand what's going. Yeah. So we are at equilibrium and we are in the stationary phase. Sorry, stationary phase. Stationary frame. Okay, so now I go to the frame and I make it rotating frame. And we do this to negate the effects of B naught, which we have learned enough right now. Now I'm going to apply a 90-degree hard pulse, where after the application of the pulse, an on-resonance magnetization doesn't change as a function of time, and therefore it remains static. And if, of course, there is always precision about B naught, which comes up when we go back to the stationary frame or the lap frame. This is where we were. Okay. And whatever you're trying to measure is actually shown on the top right as a sinusoidal oscillation. Currently, I have set no relaxation for T1 or T2, and therefore what is happening? Neither the transverse magnetization is dying, nor is the longitudinal magnetization recovering, since the relaxation is not being kept up. But remember, in real life, this is not an equilibrium state. Whenever you created a non-equilibrium state, it tries to go back to equilibrium. When it's trying to go back to equilibrium, what happens? Many mechanisms happen that destroy what you have created. For instance, you see that you have a projection along this yellow plane that's moving around. The length of the vector decides the maximum amplitude you see on the top right of the graph here. Okay? And that the maximum you could achieve ever is m naught, based on the total amount of magnetization, bulk magnetization you can ever create. Are you asking what these oscillations are, Deeptanu?
Yes, sir.
Okay. Now let's go back to the lap frame to answer your question. Let us say you're keeping a coil. Remember, the coil doesn't move. Okay. Let's say that I keep a coil here. I'm not able to keep it, but I'll just hold it. Let's say I keep a coil here. You realize that the magnetization keeps cutting this coil.
Yes, sir.
Therefore induces a current.
Yes, sir.
And this current is going to be modulated
Oscillating.
based on how much. Yes, it's going to keep oscillating. Maximum 0, minimum 0, maximum. Do you see that? When it cuts exactly, it's going to be maximum. When it's opposite to the coil, it'll be negative, and when it's orthogonal to the coil, it'll be 0. Does that make sense, Deeptanu?
Yes, sir.
Okay, so that is how you get the oscillations, and the oscillations are with respect to an omega RF that you apply. In this case, you can only simulate omega RF equal to omega naught, which is on resonance. Okay, although you still get the oscillation, they're trying to show mx in the lap frame, and therefore you see the oscillations. But in reality, if you go to the rotating frame, you're only going to get a constant number. So let's say I keep the coil here. You agree that I'll keep measuring a constant number, not an oscillating this thing? Oscillating, I mean, apparently
It
the
should be
current will not be
oscillating.
oscillating because we are in the rotating frame, right?
Will there? Yes, the current will still be there.
Yes, it will be there, but it'll appear as though it's a constant current that you're getting. Oh my God. It'll be a constant current that you're getting, right? Now, the reason why the exponential decay happens is because you have R2 relaxation. You slowly realize that the vector gradually goes to 0 on the transverse plane. Why does it go to 0 on the transverse plane? Because the equilibrium state for the transverse magnetization is no magnetization. and you have created a non-equilibrium situation. Slowly it goes back to equilibrium. And therefore you have an exponential decay, and therefore the oscillations keep getting dampened as a function of time. This phenomenon is not new to you. I'm sure you have played with oscillating pendulums back in some of your courses, where you would have started the oscillation, but over a period of time, the bob would come to a relative rest position where the energy is minimum. Correct? Deepan, you keep yourself unmuted, please. Yeah, do you agree that
Yes,
therefore you're
yes, sir.
going to get the bob back to equilibrium, right? That's the same thing
Yes,
that
sir.
happens. Of course, here this is the wrong simulation because I didn't set T1 relaxation. If I set T1 relaxation, then the longitudinal recovery would also be observed. The reason why we are simulating only with one or the other is so as to make you guys understand what is the effect, how will the magnetization change as a function of time. And remember, the entire class so far we are looking at how does dm, rather how does n change as a function of time, dm or dt, and that's what this simulation is trying to show. Okay, now let's repeat the same experiment where you start back in equilibrium and I set a certain transverse relaxation and a longitudinal relaxation time. You hit equilibrium and I apply 90-degree pulse. You realize that the length of vector is reducing and the longitudinal recovery is happening simultaneously. On the top right, you have a free induction decay that keeps getting dampened based on the transverse relaxation rate. Okay. I don't know whether I answered your question, but I hope I made things a little more clear. If you're still not clear, please ask me a little more clearly. What is that you want me to explain?
Yes, it's yeah, I got it. Like, but when you go to the rotating field, like the current will still be oscillating, right?
Irrespective of in the rotating frame, the current will not oscillate if you're on resonance.
Okay.
Okay, let's do it. I think you asked a very good question. Let's try to look at the free induction decay for CH3, CH2, and OH that we have assumed. We set the carrier on CH2, isn't it? For the example that we took.
Yes, sir.
For that one, it's just gonna decay. M naught will decay as a function of time. Okay. If you look for the same thing for the CH3, which has a negative offset, and remember it's a 2 ppm offset, so 1000 hertz is what we are looking at. I'll just try to represent it, where it's going to have its own decay happening. See, the decay rate here is given by R2 of methyl group. The decay rate here would be given by R2 of CH2. Okay, well, the oscillations will be 1000 hertz because it's about 1000 hertz offset. On the other hand, when you look at hydroxyl will also have an oscillation. Okay, and its R2 will be R2 of the hydroxyl, the rate at which it decays. And more importantly, the oscillations will be lesser just because the example that we took, we assumed it's 500 hertz away from the carrier. Okay, all these
Yes.
three free induction decay will get added up. This plus this plus this, and you will get something like something weird. I tried to draw something weird because remember, there will be frequency that constructively and destructively interfere between these. So you would not be able to see something as evidently as we would want. And you would actually get a free induction decay that looks like this. Okay, maybe I'll show an example today to make things clear. So M as a function of T. This is what makes NMR a linear technique. Just sum total of the time domain signals will be a sum total that will give you the FID, which when you Fourier transform will be the sum total of frequency domain spectrum. Remember, this is going to give a peak at minus 1000 hertz with respect to the carrier. This is going to give a peak at 500 hertz with respect to the carrier. And therefore, you're going to get three resonances, one at 0 hertz, one at plus 500 hertz, one at minus 1000 hertz with respect to the omega RF that you applied as 500.00. What is that? I forget it. I wrote a number, na? Very small kilohertz will turn up. Where is it? Yes. With respect to this, CH3 will be minus 1000 hertz. With respect to this, OH will be plus 500 hertz. Okay? And the only reason why you did not get an oscillation for the methylene group is because you kept it on resonance in the rotating frame. So in the rotating frame, it appears as though you don't get any oscillations for the on resonance peak. So what we are going to do right now is to run the experiment. My dear colleague Rajveer is there in the spectrometer and he is trying to help us insert a sample in. This window that you're seeing to the right, where I hope you're able to see the white mouse, is where you would see the lock for the NMR spectrometer. And you see the red and the green line oscillating left and right. Don't worry about why it's oscillating, why it's red and green. And in this part of the spectrometer console, you see whether a sample is in or not. Right now, it's saying a question mark. Once the sample is in, you will see kind of perpendicular lines to the sample, which says the sample is in. And of course, the lock may increase based on what is the overall, whether the lock is close enough and whatnot. Let me see. Let me make sure the position, the name of the sample I'm putting in is right. Okay. So, all right. I think the sample is in. Rajveer, am I right? Yes, sir. Okay. I'm going to take it up from here. And if I have any questions, I'll call you. Thanks, Rajveer. Okay. Thanks. Bye. So I hope the students are able to see the spectrometer and my screen that I'm sharing from my laptop. Right. Now let me open a data set. There's a data set that I should have set up yesterday. Okay. Okay, the first few series of steps that I'll be doing will be not making much sense to you. Don't worry about it. The step that you have to do is something called locking the sample. See on the bottom right of the lock window, you would see oscillations that come up. This is the time where the omega naught of the spectrometer gets fixed based on the deuterium solvent that you have in the sample. Although you may want to call this a 700 megahertz instrument, remember, so there you go. You start to see the oscillations. It takes care of the deuterium frequency. Based on the gamma, it sets the necessary frequency for the proton. Okay. And as you are able to see, although we call it a 700 megahertz instrument, it's 700.1333080 megahertz. And we go until this decimal because we get very high resolution until the hertz, and therefore you end up getting something like this. So that's the lock that is coming up. Although this sets the frequency, this still doesn't ensure that the pulses are applied at omega RF. And in order to do that, we need to do something called tuning and matching. Just to give a perspective, people who would have learned physics in the 12th standard may remember something called a tank circuit, where you have a capacitor and a inductance coil, which when the L and the C component of it, the inductance and the capacitance are carefully set, then the omega, which is given by 1 over root LC, can be optimized. So you change the L and C in the tank circuit so as to get a certain frequency. And here what I'm trying to do is to take care of similar such parameters where the total impedance, if you may remember, Z as the impedance, it will be the square root of sum of squares of the inductance and the capacitance. And basically, whenever I'm touching some of these circuits, that's what I'm trying to do. Of course, you can always tune match all the 3 channels. And this is something called a wobble curve, where the difference of the dip of the wobble curve from the y-axis indicates how off is the matching. So first you match the impedance. So as I keep changing the values, you will see that the blue curve keeps right now it's moving away, and I have to move it closer and closer to 0. That means I'm on whatever I was doing, I was going in the wrong direction. So don't worry about these steps if you don't understand. These are the essential steps you have to do before you set up an experiment. And you'll soon understand this when we go to the practical aspects of the course. So right now I'm matching the impedance with minimum impedance being achieved when this goes to 0. The red line indicates the precession frequency of B0. Now that matching has been done where there's a minimum difference in the warp curve, you would want to do something called tuning right now, where the dip has to match the red line, because the red line got decided from the deuterium that is present in the signal. So there you go. So now you have minimized the impedance and matched the frequency such that the minimum of the curve, remember 0 is here in this line and it has touched 0, indicating that you have tuned and matched. So you save this, and then the next step that you do is what's called shimming. I'm going to do an automated shimming protocol. This helps the homogeneity of the magnet around the sample being taken care of. Now, I'm going to show you the pulse program. It may look a little complicated. Don't worry about it. So this is an experiment which has a DNA sample in water. And this is the pulse that we are talking about. If you're able to see the P1 that is at 11.5 microseconds. And then you have two pulses right after it with a delay in the middle. These are called gradients. Currently, I want you guys not to bother about this part of the experiment. Whatever is encompassed by the green arrow right now, do not worry about it. For all practical purposes, you can imagine it's a single pulse that you're applying and you're trying to get the pre-induction decay. So far, so good. Everybody in line?
Yes, sir.
Okay, great. So now what I'm going to do, one thing that I've done is that this pulse, I have an inbuilt variable, which is a constant 1. So basically, if this has to be a 90-degree pulse, if I set constant 1 to 1, it will be 90 degrees. And if I set constant 1 to 4, it becomes 4 times 90 degrees, which is 360 degrees. So let me just do a very simple experiment where, let me check. No dummy scans, only one scan. Let's take a look at the spectrum. So I'm just starting the experiment. This acquisition window, you would see that the lock level changes because this experiment has something called gradients. Just starting the experiment, you would see when the experiment starts to run, how much time is remaining. There's a one scan experiment, and then that is the FID that you end up getting. So what we did right now is to excite the sample, and you got the free induction decay. Let me focus on the free induction decay, and you're able to see oscillations that are present. We will go into more details of this a little later. These are actually not continuous lines. These are actually dots. Why are the dots not coming? These are actually data points. There's a point here, there's a point there. It's just adding a straight line between them. I'm not sure why the dots aren't coming. But anyway, that's besides the matter. I hope you guys are able to understand. This is the time domain signal that you got, that you get, and then you do something called a Fourier transformation with exponential function and with phase correction. And it happens in such a way that my phase is already very close, but you're able to see the phase is not good, meaning that the lines look very good here. On the other hand, if you see the lines which are more downfield shifted, look a little skewed from the baseline. Yeah, this is something called phase correction, which you would be able to do from this part of the window. Don't worry if you don't understand what I'm trying to do. All I'm trying to make you understand how does the spectrum come, and these are steps that are rather easy to take care of. It's a little difficult to do this remotely, but I'll try my best to do it. There you go. Now that I've phase corrected, there are no surprises. The largest signal that you see here is from the residual water, meaning that we suppress water in the scheme. Just a moment earlier, I told you, do not worry about this remaining part of the experiment. You guys remember that? Yes, no?
Yes.
Yeah,
Yes.
please speak because I'm talking to a wall. It helps when students reply back. This part of the experiment helps in suppressing water because we don't want water because water is at 5 orders of magnitude higher. So we're trying to calibrate the pulse and I've set it close to 11.5. Now what I will do is that I'm not sure whether it's close to 90-degree pulse. What I'm going to do right now is I can change constant 1 to 2. What does this do is that you will see the 11.5 would now become 23. Okay, so right now the first pulse has become 23. If my pulse width of 90 degrees is right, then for this experiment, I should get 0 signal. So I've started the experiment now. Let us see how much amount of signal that we get. Okay, first thing that you get is an overflow. That's because of water, which is why you should not be calibrating on the 180 degrees when water is present. I'm sure you guys saw the error message. So I just go away and say maybe I'll put constant 1 of 3, which will be 3 times of the 11.5, which will be like 34.5 microseconds. So you guys are able to see that, right? I set it to 34.5. Effectively, if my 11.5 is right, there should be a 270-degree pulse. Let's see what we get. That means we should get our signals exactly negative from where we started. But as I said, the function, sine function, is not very sensitive at 90 or 270. Okay, and therefore, although you get this, I'm really not sure whether it's a -1 or what you got there. So I would rather calibrate it close to 360, where I set the constant 1 to 4. There's a custom written pulse sequence. In the regular pulse sequence, is constant 1 will not be the variable flip angle. But now, if the 11.5 microseconds was right, I should have gotten 0 signal. Do you guys see some small residual signal being present?
Yes, sir.
Yes. So therefore, my pulse width is a little longer. Currently, I've set it at 11.5. Now, just for the sake of it, I'll show you at 11 what is going to happen. Okay, if my pulse width is between 11 to 11.5, let's say 11.3, if I do 11, then you're going to get negative signal, meaning that you're still less than 2 pi. And this is slightly higher than 2 pi. Let's see what we get. There you go. So prediction was right, right? So therefore, I play with this P1 variable until I see a 0 crossing. Let's see, I've set it to 11.3. Let's see what we get. Okay, I hope you guys are able to appreciate the signal is almost 0, but not 0. There's still some negative component. These are the off resonance effects. You see that these are negative and these are positive. That's largely because we have kept the carrier on water. And therefore, we have to only look at resonances close to water and what is their sign. It is still negative, so I'm going to go a little longer, 11.35. Let's repeat it. It's 9:53, so I'll have to stop in 2 minutes. Here, they've almost gotten 0 signal. So it's between 11.3 and 11.35. I'm going to leave it there. And therefore, what I'm going to do is to set the constant 1 back to 1. And I have to calibrate some of the soft pulses. Don't worry about what the soft pulses do. They effectively suppress water. That's more than enough for you guys to know at this point of time. I'm changing the power based on it. This is the B1 part. Okay, these pulses, Deeptanu, you were asking today, how does the B1 work? All that we are trying to do is to play with the B1, where the B1 of this pulse is much less than the B1 of this pulse. Although in this graph, it tries to show these are one and the same. In reality, they aren't, because the wattage that you see is 1.82 milliwatts. On the other hand, the wattage that you see for the heart pulse is about 9.6 watts, 3 orders of magnitude higher, close to 4 orders of magnitude. Now that is done. When you run the full experiment, you end up getting the spectrum at the highest sensitivity. Okay, there you go. We got wonderful resonances. Here we are looking at a DNA that is base paired, and these resonances will only show up in these downfield 10 to 14 ppm if there are base pairs being present. Okay. All right. I think with this we should stop the class.